Welcome to this explainer. Today, we're going to master a really fundamental concept that quietly governs so much of our daily lives, and that is linear inequalities. We're going to break down the core formulas, the essential rules, and the exact methods for graphing them. By the end of this, you'll see exactly how these mathematical imbalances actually work in the real world. So, here is our roadmap for today. Part 1, Beyond Equal, Introducing Inequalities. 2, the symbols and formulas. 3, the golden rule, flipping the sign. 4, graphing one-variable inequalities. 5, graphing two-variable systems. And finally, part 6, real-world applications. Okay, let's just jump right in. Say you have exactly $50 for a shopping trip. You know you don't have to spend exactly $50, right? You just can't spend more than $50. Well, not unless you want your credit card declined at the register. If you have ever done that kind of mental math where you're adding things up as you walk down the aisle, congratulations. You actually already understand the foundational logic of linear inequalities.
That brings us to Section 1, Beyond Equal, Introducing Inequalities. Simply put, a linear inequality is an algebraic statement that compares two linear expressions. But instead of a perfectly balanced equal sign in the middle of your formula, it uses inequality symbols. And it's called linear for a very specific reason. The highest power, or exponent, of our variable is exactly 1. So you won't see any squared or cubed variables here. Fundamentally, we're looking at a non-equal comparison. To really get this, think of the linear inequality formula like an unbalanced weighing scale. While a standard equation demands perfectly balanced scales where the left side perfectly equals the right side, an inequality represents a state of imbalance. One side is inherently heavier or mathematically larger than the other side. Moving on to Section 2, the symbols and formulas. Notice the visual logic of the symbols themselves. They're actually incredibly intuitive once you see it. The wide, open side of the symbol always faces the larger value, while the small, pointed side always points toward the smaller value. Just remember the classic trick from grade school. The open mouth always wants to eat the bigger number. It makes reading these formulas a breeze. So we have less than and greater than. We call these strict inequalities because the two sides absolutely cannot be equal. But notice the symbols that have that little solid line underneath them? That little line is basically half of an equal sign. It means the formula is saying less than or equal to or greater than or equal to. It allows for the possibility of perfect equality right alongside the imbalance. Here is the crucial difference. A standard linear equation, like 2x plus 1 equals 5, has exactly one specific solution. X is 2. End of story, right? But a linear inequality formula, like 2x plus 1 is greater than 5, unlocks a complete range of solutions. X could be 3, it could be 10, or it could be 1,000,000. We are no longer looking for just one number. We're hunting down a whole universe of numbers that make the statement true. Now for Section 3, the golden rule. Flipping the sign. The really great news here is that solving a multi-step linear inequality uses the exact same algebra you already know from solving standard equations. You simplify the expressions, you use addition or subtraction to isolate the variable, and then you multiply or divide to get that variable completely by itself. You literally treat that inequality symbol just like an equal sign, right up until you hit one specific, vital hurdle. And this is the golden rule of inequalities. Negative equals flip sign. If, during that final step of isolating the variable, you multiply or divide both sides by a negative number, you absolutely must reverse the direction of the inequality symbol. Why? Well, because multiplying or dividing by a negative effectively reverses the order of numbers on the number line. Let's look at how this works in practice. Take the formula 5 minus x is less than 4. First, you'd subtract 5 from both sides, which leaves you with negative x is less than negative 1. Now, to isolate x, you have to divide both sides by negative 1. And right there, boom! Because we divided by a negative, the less than sign completely flips to become a greater than sign. So your final answer is x is greater than 1. If you forget to flip that sign, your entire range of solutions will be exactly backward. All right, Section 4, graphing one-variable inequalities. Because an inequality with one variable gives us a single continuous range of answers, we can visually map it onto a simple one-dimensional number line. The rules for this are really straightforward. If you have a strict inequality, so just less than or greater than, you place an open hollow circle on your boundary number. That shows the number itself is excluded.
But if you have an or equal to inequality, use a closed solid dot to show that the boundary number is included. From there, you just shade the number line to the right for greater than, or you shade it to the left for less than. So for a strict inequality, like x is greater than 3, you draw an open dot at 3 and you just shade everything to the right off into infinity. But for a non-strict inequality, like x is less than or equal to 2, you'd place a solid dot at 2 and shade everything to the left. Those shaded parts of your number line, they perfectly map out every single valid number that satisfies your formula. Which brings us to section 5, graphing two variable systems. Now, when your formula has two variables, an x and a y, your boundary is no longer just a single dot on a line, it's an entire line on a coordinate plane. First up, you isolate y on the left side of the formula. Then, you draw your boundary line. And just like the dots on our number line, we use a dashed line for strict inequalities and a solid line for those or equal to inequalities. Then, if y is greater, you shade the entire graph above the line. If y is less, you shade below it. Now, if you have a system of multiple inequalities, you graph all of them on the very same plane. The true solution to that whole system is the specific overlapping region where all of those shaded areas intersect. It's like a giant puzzle coming together. Finally, section 6, real-world applications. You might be sitting there wondering, okay, who actually uses overlapping shaded graphs in the real world? Well, massive industries do. Businesses use these exact systems to control their inventory, to plan production runs, and to maximize their profits. By taking real-world constraints like time, money, and materials, and turning them into a system of linear inequalities, logistics companies can literally save millions of dollars a year on fuel. They do this just by finding that exact overlapping shaded region of optimal delivery routes. It's a whole branch of math called linear programming, and it is absolutely crucial to modern business. So I want to leave you with this question to ponder as we wrap up. What is one linear inequality that you successfully navigated in your life today without even realizing it? Maybe it was ensuring you had enough gas to commute, or checking that your carry-on bag weighed less than the airline's strict limits. These formulas really are everywhere, and once you master the rules, you start seeing them all around you. Thank you so much for joining this explainer, and keep observing the math hidden right there in your daily routine.